This is lesson 2.4, sketching graphs of rational functions. In this lesson, the focus will be on graphing these rational functions without the use of technology. So rather than using a program like Desmos.com, we'll be referencing what we learned in our previous lesson and doing it by hand. So I've broken this down into 4 different steps for you to consider. The first step, what we need to do right here, is we need to determine are there any non-permissive values of x. Once we've determined our non-permissive values of x, then we'll be able to figure out if there's a common factor situation where there might be a hole, or we'll just have, which is more common, our vertical asymptotes. Next, after that, we will look at the degree of the numerator and denominator to determine if there are any horizontal or oblique asymptotes. And then finally, once we have figured out our asymptote situation, we'll look at the behavior of the graphs near these asymptotes, and then we'll consider our x and y intercepts. Okay, so we have a couple of examples. We'll be referencing these steps through the various examples. All right. So example number 1 here says to sketch the graph for the function y is equal to x squared minus 5x plus 4 all divided by 1 minus x. And then once we've gone and sketched this function, remember it's just a sketch, so we're trying to be as accurate as we can, but it doesn't need to be completely perfect. Once we do all that, then we'll figure out, of course, what the domain and range is. So, like most of the functions that we've been dealing with, we need to factor whenever we can. Notice right here that we have a quadratic, so we'll factor that quadratic to start. So when we factor this, we are looking for numbers that multiply to give us 4 that have a sum of negative 5, and that, of course, is x minus 4 and an x minus 1, like so. Okay. Now, here's a situation where we need to figure out, is there a common factor situation? Well, are there any of these factors that are going to reduce? Notice that x minus 1 and 1 minus x, they're completely opposite. The x is positive here and negative here, a negative 1 and a positive 1. In that case, what we can do is we can factor a negative. All right, in this case, I'm going to factor the negative from the, it doesn't really matter, but I'll do it from the denominator. And when you do that, what that's going to give you is we're now going to have x minus 1 like so. All right, so if you can imagine me taking a negative out of this 1 right here, it makes it now negative 1. And taking a negative out of that negative x makes it a positive x, and now I have this negative out in front. Now, because I've done that, these will reduce. Those are common factors. So because we have a common factor, this is going to create, so I'll just put a little arrow right here, that we have a hole at x equal 1. Okay. Now, we of course know that this would be our restriction right here, looking at the denominator, that x cannot equal 1. And often when that's the case, as you may recall, we're going to have a vertical asymptote. But because we have that common factor right there, that's going to produce a hole in our graph. Okay. So if you take a look now, well, what do we have left with this function? Because we have that common factor, we now just have y is equal to negative x minus 4. And if we distribute that negative and put this into y equals mx plus b, we have negative x plus 4. Of course, negative x or negative 1x as my slope, and my y-intercept is 4. So if we want to now, we can go and graph this thing. So we have just a regular linear function where our y-intercept, of course, was at 4. So I'll put my dot at 1, 2, 3, 4. And then we have our slope. Our slope's going to go down 1 over 1, like so. And if you take your straight edge here, I'm just going to kind of do it by hand and being bad. But you will have a function that looks like so. But when you get to 1 right here, remember what happens at 1 is we have a hole. So I'm just going to put a little dot right there just to show that that value does not exist. And so that's what our function would look like. Okay, so of course we have no value right here at x equals 1, and that was because of the common factor situation. The last thing that we needed to consider, if you recall the original question, was we had to deal with our domain and our range. Well, fairly straightforward for this question. What do we have here for my domain and range? Well, we have x values everywhere except at this one value right here. So we'd say that x can be anything with the exception that x cannot equal 1, right? That's where that hole is in our function. And the corresponding y value, this value right here, we would say for our range is that y cannot equal, what is that? That looks like it's at 3. Okay, any other values of y are good to go. So for this question right here, we didn't need to get too far down with our steps right here. In order to graph this, we didn't really have to consider are there any horizontal or oblique asymptotes. The x and y intercepts were taken care of, and it's very simple. Okay, so this was a rather easy example. Let's move on to something that's a little bit more daunting. Example 2 says sketch the graph for the function y is equal to negative 2x squared all divided by x squared minus 25, then state the domain and range. Well, just like we did with the last function, we need to figure out if there's anything that we can factor. And hopefully something is ringing a bell right away here, in that the denominator right here is a difference of squares. So this I'll factor as being x plus 5 and x minus 5. Okay. Quite clearly here, you'll likely see that we're in a situation where there is no common factors. So because there's no common factors, we can say that there is no holes. Okay, so because of that. Now, because there's no holes, then likely what we're going to have here is we are going to have, because of this information down here, we know that x cannot equal plus or minus 5. So we will have vertical asymptotes right here. So these essentially are going to end up being our vertical asymptotes. So the vertical asymptotes, if we want to be more specific, the vertical asymptotes will be these lines at x equals 5 and x equals negative 5. Okay. So this question implies now that we need to go and search for any any horizontal or oblique asymptotes. So the way we do that is we need to take a look at our degree. So the degree of this function. Well, what do we have in the numerator? Notice the numerator is of degree 2. The denominator is also of degree 2. So we would say that the degree is such that the numerator is in fact equal to the denominator. And in this case, when they're equal to one another, all we really care about is the coefficients. And so I'll write a little kind of sub-note right here, but the leading coefficient of the numerator is, as you can see right here, negative 2. And the denominator really doesn't have kind of an easy to see leading coefficient, so we just assume it's a 1. So the denominator is 1. Therefore, the equation of our asymptote, it's not going to be oblique. We're going to have a horizontal asymptote, and it's going to be y is equal to my numerator, negative 2, over this value, which is in front here, 1. And so negative 2 divided by 1 is just y is equal to negative 2. So this right here is going to be my horizontal asymptote. So we now know where my vertical asymptote is. We know where my horizontal asymptote is. So let's go and deal with that. We'll just kind of sketch those in on our graph down here. So if you recall, I'll do this in pink right here. We have a vertical asymptote. I believe they were at plus or minus 5. So just put a dot right here to indicate those. And then we'll sketch them on in. So we have a, whoops. So we have a vertical asymptote right here. And we have our other vertical asymptote right here. Okay. And we also had a horizontal asymptote. If you recall, the horizontal asymptote we figured out was at negative 2. Okay. So that gives us a little bit of an idea of how this graph is going to look, but perhaps not enough. And so what we're also going to do, in addition to doing or dealing with our asymptotes, is we're going to look at the behavior. So I'll just title this the behavior near the asymptotes. Okay, and so what I'm going to do is I'm going to set up a t-chart for me. So we have our x and our y, and what I'm going to look at is I'm going to look at values that are very close to our asymptotes. So let's deal with our vertical asymptotes first, kind of to the left of our asymptote and to the right of the asymptote. So this was at negative 5, so I'm going to look slightly to the left at maybe negative 5.01, and then I'll look kind of to the right at maybe negative 4.99. And now what you would do physically right here is you take this value and you put it back into our original function, so this function right up top here, and you would see what your calculator generates. And so I've already taken the time to go and do that. And when you do that, when you put negative 5.01 in for x, you end up getting approximately negative 501. And so these are just approximations. And so all that we're seeing right here is that that produces a very big number. All right. When you go and put in negative 4.99, you get another very big number, only this one is positive. Okay, negative 498 point something. And again, these are approximations. Okay, so that's what's happening right here. So what this means is very, very close to this asymptote, but on that side of the asymptote, the value is very small. And on this side of the asymptote, the value is very big. Well, let's take a look at this asymptote right here. My guess is that we're probably going to see some symmetry. If you take a look at maybe if this is at 5 at positive 4.99, so on this side of it, and then maybe at 5.01, you're going to see that we get the values that we expected that are very, very similar. So this one gives me 498, and this one gives you negative 501. So again, on this side of it, it's very positive, and on the other side of this asymptote, it's very negative. Okay, so that's all fine and good, but let's take a look at also what's happening near this this horizontal asymptote. In order to do this, what I'm going to do is I'm going to see what happens to my values of x as they get very, very large in the positive direction, so going in that direction, and in the negative direction, going in that direction. Okay, so in order to do that, I'll just, you could pick whatever you want to put into your calculator. I'll pick 100, I think it's big enough, and I'll pick negative 100. So that's my big positive and my big negative. And again, I've taken the liberty of doing this already. And when you do it, what you end up seeing is as the values gets bigger or smaller, it approaches this asymptote. So the value that I end up getting was negative 2.001, I think it was, for both of them. And so what that means is as the values get bigger and smaller, it's getting closer to that. Okay. The last thing I would like you folks to always do is to consider our x and y intercepts. And if you remember way, way back, probably even to grade 10, we can always find out our x and y intercepts by simply substituting in 0 for x or 0 for y. Well, this one's kind of interesting because when you substitute 0 into our function right here, for x, let's say, notice what happens. You're going to end up getting 0 in the numerator, all divided by, heck, we don't even care, although it would be negative 25. 0 divided by negative 25 gives you 0. Well, this one's kind of interesting because what that means is that the x and the y intercept are right here at 0, 0. So that's another ordered pair that you could add, like so. And if you want, you can always add more points. You can just even put some random points if you're wondering what's going on. So now that we have all this, we should be able to, within reason, give ourselves a little bit of a sketch. So if you recall, at negative 5.01, the value right here was very negative. Okay, and then we saw that this value a little bit past the asymptote was very positive or very high. So what we can imagine is that as the values get bigger and bigger, they're bounded by both of these asymptotes. We're going to have something that's going to look like that, and then it's going to look the same on this other side, give or take. Okay, and if you remember, on the inside of these two asymptotes right here, the values were very big, so very big kind of here and here. We know it's going to go through 0, 0 like this, and so you might want to take a look at a couple of values. But give or take, you're going to have a graph that's going to look like this. Okay, so again, a very rough sketch. If you want to put some extra values in to see what's going on, if you weren't really sure, maybe you were confused, maybe you thought it might go down to this asymptote right here and then come back up and hit that point and then come back down, who knows? You might just want to try some extra points, but this would be satisfactory for me. Finally, just like in the last example, we need to determine our domain and range. And so I'll try to fit that down just right at the bottom right here. So domain and range, super quick. Domain, what values of x do we have, and our range. Let's take a look. Well, fairly straightforward. Notice that we have all values of x with the exception of our asymptote. So we say that x cannot equal plus or minus 5. And for our range is very, very similar. It's just that we can't have values at negative 2. So we'd say that y cannot equal negative 2. Okay, so that finishes that example. Let's go and take a look at example 3. Example 3 says, sketch the graph of the function y is equal to negative 2x squared plus 5x minus 2, all divided by x minus 1, and then we will end off with stating the domain and range. So like we did before, we always are going to start off with trying to factor. In this case, we have a decomposition, or as I call it with some of my students, we have an AC method factoring that we need to do right here. So let's do that kind of over on the side here, and then we'll go and we'll write it in factored form up here. So a times c is going to give you positive 4. So we have ac is equal to 4. Numbers that multiply to give you 4 that have a sum of 5 are 4 and 1. So those will be our two magic numbers. This gives me negative 2x squared plus 4x plus x minus 2. So we split the 5x into being the 4 and the 1. What can you factor in the first two terms? You can factor a negative 2x, which gives me an x minus 2, and an x minus 2 right here, which of course gives you a positive 1. So my two factors are negative 2x plus 1 and x minus 2. Okay, so I can rewrite this function as y is equal to negative 2x plus 1, x minus 2, and an x minus 1. So I think it's fairly clear to see here that we are going to have, first thing we can say is we have no common factors, nothing that's going to simplify in the numerator and denominator. So therefore there's going to be no holes in the graph. We do have a restriction. So the restriction, of course, from here is that x cannot equal 1. So we are going to have a vertical asymptote. At x is equal to 1. Okay, so we can definitely go and graph that. And the next thing we need to tackle is, are there any horizontal or oblique asymptotes? And so in this case, you'll notice that the degree, so let's write that down, the degree of the numerator, so last time we had them being equal to one another, if I recall, this time you'll see that the numerator is greater than the denominator. And so when that is the case, we are going to have an oblique asymptote. But specifically, where is that oblique asymptote going to be? Well, in order to figure out where that's going to be, we're going to do a little bit of synthetic division. So let's go and do some synthetic division down here. In order to do synthetic division, we will take a look at our divisor. So our divisor in this case, if we look, is x minus 1. So I'm going to put a positive 1 outside right here. I always like to indicate a plus sign, if you recall, and I have my remainder like that. And then we need to consider our coefficients. So I go back up to my original function. I have a negative 2, a 5, and a negative 2. So I'll write those in. Negative 2, 5, and negative 2. And then we will drop down the first term. That's what I always like to do with the arrow right there. And multiply it on through. So negative 2 times 1 is negative 2. When you add those terms together, we have a 3. 3 times 1 is 3. And we have a remainder of 1. Okay. So right here, what we now know is we have a quotient of negative 2 and 3 right there. So we can say that our quotient, which essentially is our oblique asymptote, is the equation y is equal to negative 2x plus 3. Okay, so that is essentially my oblique asymptote. And now that I have that jazz, let's go and just take a look at what this would look like. Okay, so I will graph this information. Again, I'll use my my pink line for my asymptotes. We had an asymptote of x equals 1. That was my vertical asymptote, so I'll put that in there. Alright, so that's good to go. And the next thing we need to do is we'll do our oblique asymptote. So that's what we just had up here. That was a y-intercept of 3 and a slope of negative 2. So 3 and negative 2, so down 2 over 1, down 2 over 1, and so on. It's best to use a straight edge for this, although I'm going to just kind of sketch it like that. Okay, so remember, our graph will not cross those lines. All right. So again, just like we did before, we're going to look at the behavior, because just because we have those asymptotes doesn't really mean we have any idea what the graph looks like. The behavior near these asymptotes. Okay, so I'll set up my t-chart, and we'll try to key in on a couple values. Now, the values I'll key in on is, first let's start with the vertical asymptote right here, and that's really the only one we need to consider. I'll consider values to the left and the right of it. So this is at 1, so I'll consider maybe 0.99 and maybe 1.01, at least to start. So now that you see that, what we're going to do then is we have those values of x. You substitute those into your original equation. So I'm talking the equation right back up at the top right here. And we see what your calculator is going to spit out at you. I've already done this, and when you do that, you end up getting a fairly big negative number for the 0.99. So it gave me negative 98.98, and for the value on the other side, it gave me a fairly big positive number. I think it was 100.98. Okay, so to give you an idea what that means that right here for that value of x, for instance, it's very, very negative, and for this value of x on the other side, it's very, very positive. Okay, so my graph, I'm not really sure what's happening kind of in there, but it's very, very close to that asymptote and very, very close to that asymptote in the positive and, of course, the negative direction. Okay. The next thing I would get you to consider is for this equation, and maybe I'll just write the equation down here so that you guys can see it, but it's y is equal to, just so that we can reference it again, negative 2x squared plus 5x minus 2, and then we have the x minus 1. Okay, so we've got our equation there. Let's go and find some additional points. Let's first start by finding the, let's do the y-intercept first. So in order to find the y-intercept, what we simply do is you substitute 0 in for the opposite value. If you're looking for the x-intercept, you substitute 0 in for y and solve. So right here, what I will do is I substitute 0 in, and we would then have y is equal to 0 squared is 0, 0 times negative 2 is 0, plus 5 times 0 is 0, and so we just have negative 2 in our numerator, and then we'd have 0 minus 1 down here gives you negative 1, and that's going to simplify to give me 2. So that would be the ordered pair 0, 2. So that is my y-intercept. If you want, you can go and draw that point right in there. Okay, next let's go and find our x-intercepts. And in order to find the x-intercepts, all we have to do is consider our numerator right here and substitute 0 in for y this time. So this will give me 0 is equal to negative 2x squared plus 5x minus 2. And if you recall, we already went and factored this, and our factors were negative 2x plus 1, and the other one is x minus 2. And so when you set these equal to 0, the values that we end up getting for x, for the one on the left-hand side right here, if you can imagine moving the 2x to the other side of the equation and then dividing by 2, you would end up getting 1/2 and 0. And then the other one, if you move the 2 to the other side of the equation, we have the ordered pair, 2, 0. Okay, so those will give me my x-intercepts. So I'll put this one at 2, and I'll put this one at 1/2 and 0. So that would be this point probably right about there. Okay, so if we take a look at what is happening right here, it still might not give you enough, and so you still might have to spend some time taking a look and just putting a couple more points in. Maybe figuring out what happens here at negative 2, what happens here at negative 4. But if you spend some more time doing that, and just to kind of close off this lesson, what you'll end up getting is you'll be getting a function that looks approximately like this, and looks approximately like this. Okay. Just by using the information that we've taken a look at, that's accurate enough for me. Okay. So to close this lesson off, what you need to be comfortable with doing is knowing when there's holes in graphs, knowing when there's going to be a vertical asymptote, when there's going to be oblique asymptotes, horizontal asymptotes, and then finally trying to pick some key points, whether those be figuring out what's going on near the asymptotes or looking for x and y intercepts. And sometimes that might not be enough. This was a good example where you may have needed to pick some extra points to figure out what was going on in these regions. But hopefully those steps will give you enough information to get a sketch that looks fairly accurate. Okay, that concludes this lesson.